Hello, welcome everybody. My name is JD Bean. I'm Principal Security Architect with Amazon Web Services, and you are here at NIS201, behind the scenes, AWS investments in security innovation. So, a little forward about myself. When I was a bit younger, I was a stage performer. And one of the things that you learn about stage performance is that behind the curtain on the stage, there's a whole team of people that make the show go on, much like, in fact, today at this talk. And a lot of what goes on behind the scenes is all about providing a seamless experience to the audience, right? Folks who get to come and immerse themselves in something simple that brings them delight and it works for them. But behind the scenes, there's a lot of work that goes into making an easy and successful experience for an audience. And in a way, that's really what today and this talk is about. A little bit about expectations. What to kind of imagine this is going to be like over the next hour that we spend together. Is this going to be a deep dive in the AWS technologies that exist kind of behind the scenes for security? And the answer to that is not really, not exactly. I'd say it's more of a survey, a broad survey, probably an incomplete survey, but really it's the iceberg analogy here. We're going to take a look at the iceberg itself, get a sense of a little bit of what's under the surface, but there's going to be a vast world that we could continue to deep dive. And many of the topics that we cover today are things that there are talks about this year at reInvent or in Inforce, or previous years in reInvent and Inforce and our other conferences, where I encourage you, if you have a topic here that you want to go even deeper on, to investigate those materials. Now, to get us started, without further ado, I want to hand things over to my colleague and friend, Peter O'Donnell.
Hi, folks. My name is Peter O'Donnell. I'm a Principal Solutions Architect. I've been here for about 8 years now, covering some of our largest and most challenging customers. And a question we get a lot is like, tell me what's really happening. Is there a secret ingredient? How is it that you're able to scale? How is it that you're able to move quickly? And how is it that you're able to uphold this promise that security is truly our top priority? And there is a secret ingredient, but it's not what you expect. The secret ingredient, now we can tell you a lot about software and hardware engineering, but the truth is that it's rigorous, obsessive ownership. And that is what drives our security culture here at Amazon. Now, during today's talk, we are going to talk about some amazing technologies and some long-term investments that we've made to protect our customers' security, to protect our customers' data, and to maintain a level of assurance over time that we will remain secure. As you very well may know, that being secure alone is not enough. You have to have other stakeholders. Stakeholders in the form of compliance, maybe even a regulator. And being able to tell that story is essential. And the way we work this is through rigorous, obsessive ownership. So if there is one word for security at AWS, it is this deep idea of ownership. That security is truly everyone's responsibility. And the role of security is not to say no, and it's not to be the police. The role of security is to enable the business to move quickly. That is how we think, and we believe you should think that same way. But ownership by itself is not enough. It must be rigorous. And what does rigor even mean? Rigor means being unrelenting, deep diving across all aspects of security and building in security and trust into every layer. And at Amazon, we're guided by this idea of the leadership principles. When we say customer obsession, we mean it. It's not focus, it's not customer centrism, it's not customer priority, it's customer obsession. And this idea of rigorous ownership delivered with a spirit of true obsession is how we have built our company and how we have built our technologies. That security and assurance is at the heart of everything we do. It begins with our threat models. It begins with working backwards from what we want to achieve on behalf of our customers, and then working backwards to make those things true. And because security is our top priority, we are relentlessly and unrelentingly focused and obsessed with building this idea of security. And so we have this idea of a flywheel, that as we build our services and as we move to higher velocity launches, that we do so in the name of customer experience. Over 90% of everything AWS has ever built was actually built because customers asked for it. We believe very strongly in making something that people want. And as we build in more rigor and more control into truly all layers of the stack, from the hardware all the way up to the application protocols, that this idea of unrelenting, focused security review is woven into everything we do here at AWS. And this extends to the highest levels of management. Every Friday, our CEO reviews security events with the teams. That's true for our security team, it's true for our service teams. And this idea of constantly spinning this flywheel is how we get this culture of obsessive, rigorous ownership. Now, you must be familiar with this idea of the shared responsibility model, that we take care of a lot, but our customers remain responsible for a great many things.
So, right, the model of the shared responsibility model, as you'll see here on the left here, is really that AWS is responsible for the security of the cloud, while customers are responsible for the security in the cloud, right? The security of their applications, their configurations, their operating systems, et cetera. Right, on the bottom here, this orange section, you see the fundamental responsibility of AWS starts with physical infrastructure and global infrastructure, networking, and the low-level compute, storage, and database that powers fundamental AWS services. There's really two, I think, major takeaways that I want to leave you with about the shared responsibility model as we start the session today. The first is that although the bottom half of this model is colored orange, AWS is constantly innovating and expanding on the features, the services, and the capabilities that we provide to customers to help them be successful in their side of the shared responsibility model. I'm going to launch out. I'm going to start talking a lot about some of the lower level infrastructure, but I want to call back to something that was mentioned in CJ's keynote earlier today, talking about how the large investments we put into threat intelligence and the way that it comes out and benefits customers directly in services like Inspector, Guard Duty, and Web Application Firewall. These are great examples of the type of innovation and investment that we're making that ultimately play towards the customer side of the shared responsibility model. Another takeaway that's really important is understanding how the shared responsibility model will change depending upon the exact service that you're using and talking about. So for Amazon EC2, you have a great example of a service that matches to that first image of the shared responsibility model. AWS is responsible for managing the underlying infrastructure, the physical hardware, and even the operating systems and the networking that those services use. But the virtual machines, the EC2 instances, have their own operating systems and their own configurations that fall into the customer side of the shared responsibility model. The best way for customers to take advantage of and get the benefit of AWS investment and obsession and rigor and ownership when it comes to security is by using higher level abstracted services. A great contrast to Amazon EC2 is AWS Lambda, right? Our function-based service, where AWS actually takes on greater amount of responsibility for things like the operating system, and customers really are able to tighten up where they need to focus their responsibility on their own application code and configuration. So to start out with the base of our infrastructure, this is a slide that I think many in this room may have seen before, and it really lays out our overarching global infrastructure. We start with a series of regions located across the world, and each region is composed of at least 3 availability zones, which are interconnected using redundant network fiber and have a redundant external communication access outside of that region. The availability zones are developed as a fault-tolerant boundary. Right? They're developed for high scalability and high availability, and we encourage customers to use these primitives, which have been designed to be separate in terms of risk around things like power and networking and even floodplains, but to also take advantage of the fact that they have low latency connectivity to each other, enabling things like synchronous replication and real-time transactional workloads. A critical thing to understand about the way AWS architects and thinks about the construct of a region is that in most cases we're dealing with a largely independent deployment of AWS. When a customer puts their data into a region, they can be absolutely confident that the AWS services they use are going to keep that data, that customer data, in the AWS region that has been selected. And this is really critical for compliance workloads. Another point is how these regions are interconnected. A lot of our customers want to use multiple regions to meet things like data residency requirements, to serve global customers, and even in some cases for things like disaster recovery. We've maintained a redundant fiber backbone connecting all of our regions that is automatically physically encrypted at the physical layer using AES-256, a quantum-safe algorithm that Peter's going to talk a bit more later about, so that any time traffic leaves one of our secured facilities, it's going to be transparently and automatically encrypted. This backbone has a number of other security benefits. Because communication travels along this backbone, we can ensure that our customer traffic and even our own management traffic traverses our infrastructure rather than the public internet. All communication has been structured in the AWS network so that when an instance or a service hosted in AWS is using AWS's private network, packets that originate on the AWS network, destined for the AWS network, will always stay on that global network, even when they're using public IP addresses. So now let's move into the concept of networking kind of within our facilities, and that customers are going to leverage as their primary fundamental primitive. And that's the virtual private cloud. This is a private network dedicated to a specific customer. Really, it's your own private data center network. And this has a lot of benefits, right? As with many things in AWS, because you're driving the configuration and instantiation of these resources using APIs, you have fantastic visibility and the ability to automate through infrastructure as code. Because VPCs are a entirely free construct, customers are able to create multiple VPCs for multiple steps in the software development lifecycle, et cetera. But what is a VPC? So at a physical layer, we have a foundational network for our services and inside our facilities, right? This is something where we have folks who've gone extremely deep in creating scalable, resilient, and high-performance networking using custom hardware and software at all steps along the stack. But when you set up an Amazon VPC, you don't want to be in a shared network, right? The construct of the VPC is to provide you your own private network. And how do we do that? So you have two instances sitting on physical servers. Every physical server like this is going to have one, possibly more EC2 instances. And those EC2 instances, in most cases, are going to be from different customers. And we want to make sure that we have strong logical isolation boundaries between them on the network level. So the way that we do this is through attaching each of our EC2 instances nowadays to a hardware-based smart router that we're actually going to talk about a little later in the presentation. And these smart routers are able to translate IP packets coming from a customer's network into our custom-designed VPC encapsulation layer. We evaluated a number of different standard technologies in order to provide this type of experience to customers when we were first building VPC. But we ultimately found that none of them met the security, performance, and scalability bar that our customers required in AWS. So we built our own. So it looks a bit like this, right? On the inside, we have the customer IP packet which is encapsulated by our VPC layer, and finally wrapped with the physical IP headers on the bottom. Right? The IP section identifies the target physical host interface on the network, where the VPC is marking the VPC and the elastic network interface that is sending and receiving the traffic at the VPC level. How does the smart router know this? The smart router knows this through our mapping service. The mapping service has a distributed web service that is responsible for maintaining complete visibility and mapping between customer VPC routes and IP addresses and physical destinations on the wire. Obviously, the requirements of networking are extremely high. To make this scalable, we had to put in a tremendous amount of effort and refinement to support microsecond scale latencies of mapping resolution. We do this by proactively caching mappings where they're used and proactively invalidating them when they change. So what does this all mean then for VPC networking? From a security standpoint, it means that every packet flow on the network is going to be individually authorized against a rule to validate appropriateness of source and destination, both before it's transmitted and before it's delivered to the recipient. It means things like ARP packets never actually traverse a network because ARP resolution is being emulated within our smart router. It means things like promiscuous mode, although technically available, don't actually reveal any traffic other than the traffic that is bound to or from a specific customer instance operating system. And most importantly, and this is, I think, a trend you're going to hear a bit about, is that the implementation of VPC is completely transparent to customer software. You send a standard IP address. You don't have to modify your operating system, your networks, et cetera. You simply use a network driver. And all of this is taken care of by the AWS VPC system. The VPC system and AWS also provide 2 built-in firewalls to every VPC for free. You have the security group that's enforced at the layer of the instance itself, and the network access control list that's enforced at the subnet level. Now, we could talk about this for hours, and some folks have, of course, in the past. But in the interest of time, I think we'll move on to the next topic, which is a bit about encryption of data in transit. So we have a number of different places. We talked about the backbone, but also when using things like cross-region VPC peering, where you can connect a VPC in one region to a VPC in another region, there's also another level of transparent encryption that's being applied by default. This is in addition and defense in depth to the backbone encryption we already discussed. Furthermore, that smart router we talked about, which is a part of our Nitro system, also provides hardware-based encryption in transit automatically when 2 instances in the same VPC communicate with each other. And this is supported on the majority of our instance types. Although it's not transparent, we also offer things like MACsec and IPsec VPN tunnels to help customers to encrypt data in transit between their networks in AWS and on-prem. And of course, we're not going to go deep here, but there's also a number of different mechanisms for customers to put in place their own application-level encryption in transit in addition to these mechanisms. So moving from networking onto compute itself, let's talk a little bit about that Nitro system. So the Nitro system is fundamentally a reinvention of what virtualization can look like for our customers. It was a very long 10-year process of development that we've ultimately released to the public in 2017. On the left is a view of kind of classical virtualization. You have a server. On the server runs a hypervisor. If we're talking about Zen terminology, right, you have the hypervisor, and then you have another privileged operating system called DOM0. And in that section of the compute, you have things like networking I/O, storage, management, security, and monitoring. With the Nitro system, we really went to reinvent this process of virtualization to optimize for both performance and critically security benefits for our customer. What we ended up with was something that looked very, very different, where we removed the DOM0, the networking, the storage, the management, the security, and the monitoring. We removed all of that from the main system server into a new paradigm. So what is the Nitro system? The Nitro system consists of 3 primary categories of components. And the first are the Nitro cards. These are special purpose, in-house designed and built computer cards that are attached to our servers and provide the functions that we removed from the system mainboard. So the smart router that I mentioned earlier, that's the VPC networking card for Nitro card. Amazon EBS, our elastic block storage, which is a network-provided storage system, is another Nitro card. Local instance store, where you have drives that are attached directly to the physical hardware, is another VPC card. And critically, we have a system controller that now takes responsibility for management, security, and monitoring of the system. The next component is the Nitro hypervisor. This is a hypervisor that we built, designed, and customized to be deliberately minimized with a low attack surface, to provide lightweight virtualization, to provide the bare minimum, really, of memory, CPU allocation, and then to step out of the way, allowing it to provide near bare metal-like performance on a virtualized system. And lastly is the component of the Nitro security chip. This chip is integrated into the system's motherboard. It provides 2 functionalities. One is that it provides a layer of defense in depth against any writes to low-level system hardware storage devices, things like the firmware on the main server. The second, which is particularly critical, is that it enables a secure hardware root of trust. So when the system starts up, it allows the Nitro controller to come in and to validate the integrity of the system from the ground up, providing a high level of trust, integrity, and visibility into what is running on any one of our pieces of hardware when it boots. These here are the Nitro cards themselves, or a selection of them. All EC2 instance types that have been released since 2018, and some before, are powered by the Nitro system. This is something we, as I mentioned, worked on for 10 years and have been continuing to iterate on, recently announcing the release of our 5th generation of custom silicon that powers this system. Here's a couple of the security highlights. All right, I mentioned the secure boot process that allows us to have a simple, verifiable hardware root of trust to ensure that every component running on the system is known and pre-authorized before it ever touches customer data. Another is that every critical element of this system has been designed to be live updatable without impacting customer workloads. So we've removed any potential tension between patching a system and customer impact. Lastly, as I mentioned in the case of VPC, but is also the case for EBS, storage, and even networking, these cards are able to provide transparent, hardware-based encryption for storage, networking, and memory. I think one of the most important elements of the Nitro system design is its entire exclusion of any operator access mechanism. There's no SSH server or any general purpose access of any kind. In fact, there's not even a networking stack. All Nitro operations are performed via secure, authenticated, authorized, logged, and audited least privilege administrative APIs that are hosted by the Nitro controller card. And what is deeply important is that no administrative API has the ability to access customer content on the hardware. Recently, we've released a number of pieces of assurance and transparency to meet customer demand in the space. The first is a deep dive white paper covering the design of the Nitro system and its resultant security properties. The next is that we partnered with NCC Group to provide a third-party review of the Nitro system architecture, primarily focused around AWS's claims about the zero operator access portion of the Nitro system. Now, I encourage everyone to have a quick read on this. It's only a few pages long, so it's not too lengthy, but I'll give you the highlight, which is that there were no gaps found in the Nitro system that would compromise these security claims. lastly, is that we've actually gone and taken these controls, which are so fundamental to AWS and to the Nitro system itself, and actually included them now in our AWS service terms. So these are clear and published and can be reviewed at any time. Stepping away from virtual machines and EC2 and the Nitro system specifically, I want to say a quick word on compute isolation generally. AWS made a decision a long time ago that our general purpose compute services will always use a virtual machine boundary to isolate two customer workloads from each other. Now, for something like EC2, which is a virtual machine service, this is perhaps not so revolutionary. However, in the case of container-based and function-based workloads, this is not, I think, a common choice, and it's one that we feel very strongly in. To enable us to provide the density and the fast launch times that are typically associated with a container-based workload, while also offering the strong hardware virtual machine-based isolation properties of a virtual machine, we worked to develop and then ultimately open source Firecracker. Firecracker is an open source virtualization technology, an alternative, if you will, to the Nitro hypervisor that's purpose-built for creating and managing container and function-based multi-tenant workloads. Today, this supports workloads and services such as Lambda, Fargate, and Athena at AWS, and is also in use by other members of the community. Firecracker is a really innovative design. I encourage folks to have a look at it. But it's really remarkable how it's able to use its minimal device model and kind of micro VMs to encapsulate a container-based workload in an incredibly lightweight VM that can be adjusted in terms of resources and scaled out to high density, while still maintaining the hardware virtualization boundary that's so critical. Moving on from compute, I want to have Peter return to the stage to talk a bit about cryptography.
Thanks, JD. This idea of Nitro being purpose-built for this is really a revolutionary concept. I mentioned earlier about secrets. I was at dinner in 2016. A colleague leaned over and said to me, somewhat tipsy, he said, hey, the next generation of the hypervisor is going to run on ARM. And if you know anything about hypervisors, that's like a weird thing to say for an x86 workload. Something we're really proud of. I think you should learn more. Let's talk a little bit about encryption. S2N, you may remember 9-ish years ago, there was a very serious vulnerability in the community known as Heartbleed. What Heartbleed represented was a new entry point in TLS that allowed an adversary to return memory it shouldn't have been able to get. Kind of a classic computer security problem. And this kind of shocked us. It shocked the world. When we went and looked at the predominant implementations of TLS, including the ones we were using at the time, we saw a code base with 300,000 lines. It was very old. It's all C, and C is a fine language for performance. It's not amazing for memory safety. And we saw an opportunity, like we often do here at AWS, to reinvent, to reconsider what it is that we do in order to solve this problem. And so we invented something called S2N. And S2N is a completely new re-implementation of how TLS works. It's of course standards compliant, but what it is a redesign of how the handshake happens in software. Of course, it's open sourced, and it had some very particular design goals when we created it. S2N is deliberately designed to be human readable, that the code has an elegance to it, that it can not only be read and understood by humans, but it can also be understood and proven by other software, something known as formal verification, what we often refer to as automated reasoning. And this idea of re-implementing TLS gave us a lot of really great capabilities. A smaller code base, more human readable, formally verifiable, and again, open source development. I can tell you that S2N powers the entire S3 edge, something that handles a weird number of TLS connections every day, every second. And so we've continued to iterate on S2N. You're already receiving its benefit, whether or not you know of it. That's kind of the theme of this talk. And so we've continued to build on S2N, to create new implementations of Big Num, to provide better, more reliable, more performant, and safer crypto primitives for all manner of different software. We have also built a new implementation of S2N that incorporates Quick. If you're not familiar with Quick, it is the basis of HTTP3, and it's a radically new way of thinking about the total number of round trips necessary from client to server to reduce the time to first encrypted byte. It's very, very powerful stuff. And this idea of implementing Quick with S2N gives us a lot of really powerful capabilities, and we've been able to bring other additional benefits here. I mentioned this idea of verified correctness, but we're also bringing post-quantum capabilities to S2N. I'm going to talk about post-quantum in just a minute, but the short answer is that there exists the possibility of a future where a sufficiently powerful quantum computer is going to radically change the basis for some of asymmetric cryptography. But this idea of this implementation is a relentless focus on what we always are focused on, security being our top priority, and because we're Amazon Web Services, we must focus on scale and performance as well. Speaking of this focus of security, performance, and purpose-built hardware, let's talk about our HSMs. If you use Amazon Key Management Service, you're familiar with these HSMs, whether or not you've actually thought hard about it. These HSMs provide the hardware root of trust for our entire key management infrastructure. So if you create an encryption key in KMS, and then you launch new encrypted volumes in EBS, the data encryption keys used to protect that volume are themselves protected by a key that lives inside of KMS. The only time the key is in the clear or is used for a cryptographic operation is within the confines of the HSM, which is a validated module. I'm delighted to tell you that after years of working with NIST, that the KMS HSMs are now validated at FIPS 140-2 level 3. Prior to now, going back 5 years, we've had level 2 validation for our HSMs that were further validated at some very critical aspects of level 3. But I can tell you that today, the HSMs in our fleet that you are using right now are all now fully validated at FIPS 140-2 level 3. Yeah, thank you. I mean, I shouldn't say thank you. I have the privilege of saying we a lot, and I didn't create any of this stuff, but it's true that we are now validated at -2 level 3, and perhaps more interestingly, because we are long-term owners here at Amazon, we are attempting to build a business that will outlive us, that these same HSMs, the current generation of hardware that is in production today, has also been submitted for FIPS 140-3. -3 is a generational change from -2. It is the successor to the program. And these same HSMs that are recently validated at -2 level 3 have also been submitted for and now tested against -3 level 3. And we believe we will be one of the first providers to deliver a fully validated solution at -3 level 3. And it's interesting to know that these HSMs are purpose-built hardware. Some of the smartest people in the world, and especially here at Amazon, have worked on these devices over time. And all last year, while you were asleep or perhaps doing work, we replaced the entire hardware fleet. We swapped out every HSM that backs KMS with this next generation of hardware that, again, NIST is now validated at -2 level 3, and that we are now tested against, not yet fully validated, for -3 level 3. And these HSMs are awesome. They are purpose-built. They are built to rigorous standards, to not only Amazon's own very high security bar, but the FIPS bar as well, that maybe your firm or your firm's customers will expect and demand. And we believe these HSMs are the right choice for most customers. It is a secure, trusted, validated piece of hardware to not only hold your cryptographic material while in the clear, but perform correct cryptographic operations against that key material. But we always hear from customers, and we have customers who believe, or who have lawyers who believe, that the HSMs that provide their key material must live in a facility that they control, something that is not, directly compatible with the cloud. But I'm delighted to tell you, and we announced this back at reInvent, that we have a new capability called the external key store. Now, as a general matter, we don't think you should use this thing. But if you need to use it, or if your customers, your downstream customers have demanded such a capability, or if your stakeholders have demanded such a capability, to hold and control key material in your own facility, you can now do that. You can launch a commercial HSM in your own colo, in your own fancy data center perhaps, and bridge and connect the HSM that is in your house, metaphorically, to the cloud. It's a very powerful capability, and this allows our customers to have more flexibility across a wide range of regulatory regimes and localities where such a thing may be necessary, or at least believed to be important. But when we did this, we brought our same obsessive rigor to it. Because fundamentally, if we are not designing the HSMs and we hold security as our topmost priority, that means we're putting a lot of faith in the correctness of a root of trust that we don't control and that our customers arguably don't control either. So we did something very interesting when we implemented XKS. You may be familiar with the envelope encryption pattern. The envelope encryption pattern is where you have a data encryption key, I'll call that a DEC, that is used to actually cipher your data. And then that key must be protected, and it is held and itself encrypted at rest. The term of art for this is wrapping, like a present. The data encryption key is wrapped by the root key that lives in the HSM. And what we've done here with our implementation for XKS is wrap it twice. So that even if there's a cryptographic failure of the correctness or the integrity or the validity of the encryption key that lives in your HSM, it is still further wrapped by an encryption key that lives in our HSM. This works transparently, it works automatically, and it supports the core premise that you may believe that you need to control the key material in your own facility. You still do. That is why we built XKS. But we built it in a way where all of your data that now is dependent on this is still rooted in keys you control, but we've added this idea of a second envelope. And again, in the theme and the spirit of this talk, this is something you might never even know about. But take it as a testament that what we do here is rigorous and obsessive. And that's why we built this double envelope pattern for XKS. It's why we built XKS in the first place, to support our customers, particularly in Europe. So let's talk about the future of cryptography. There's a new weird thing that's on the horizon that the industry is taking very, very seriously. And let's talk about fundamentally what it means to build a cryptological solution that lasts for a period of time. That it's not enough that the cryptographic solution and its algorithms and the implementations of those algorithms are secure for the time of deployment. They must also be secure for the expected lifetime of the resulting ciphertext. Now, there's a wide range of use cases here. If all you need to protect is a session key, well, maybe that session key doesn't need to live forever, because the thing that you're encrypting is ultimately going to be invalidated after a period of time. But if you're protecting medical records, financial records, civil government records, the expected lifetime of that protected data may exceed your own. And so it's important that the crypto system used to protect this is both trustworthy and reliable during deployment, and when you actually use this thing, and it must be trustworthy and reliable for a long period of time. And what does it mean for a crypto system or an algorithm to be trustworthy for a long period of time? Well, it means that you understand all of the potential ways to compromise or attack that algorithm or that cryptological system. That means a long period of academic research to explore the algorithms in public across thousands of person hours to understand what vulnerabilities may exist in this software. And as we understand what potential attacks could be used to undermine or compromise this crypto system, we then model that against how long it would take to do. Cryptography, as you may be familiar, is largely predicated on very hard problems. This idea of a one-way function, that if you wanted to reverse it, the only good way to do it would be the hard way, to guess every key. And that's why we have such large keys. An AES 256-bit key means that there's a total number of possible keys that's like a weird number, like a dumb number, like more than molecules in the universe, things like that. But we know that there are algorithms that could work against it. These algorithms do not run on conventional computers, and if they did, it would again take hundreds of millions of years to recover the key. But there exists a possibility of a new type of computer. A new type of computer that is not binary, that does not just run on ones and zeros, but actually has a new, weirder way of thinking about the underlying primitives of compute. The classical computers that we all use today, and you may have in your pocket, those are classical computers that rely on the binary system. But this new class of computer system, known as a quantum computer, has new ways of thinking about the underlying representation of data and operations. And instead of it just being on or off, 1 or 0, there exists this new idea called a superposition. And if you're a super nerd, I encourage you to look it up online, but suffice it to say that this existence of this new type of model can give rise to performance capabilities for known algorithms, algorithms that we have been aware of for years, decades even. And what it means is that this new type of computer, if it comes into existence, there are quantum computers today, but they are not sufficiently powerful. That they can use qubits, but the number of qubits is relatively small. And in the same way that we understand that a 64-bit classical computer has power and capabilities beyond a 32-bit classical computer, that as we build quantum computers into the far future, and as they gain the capability to use more and more qubits, it becomes possible to undermine a lot of cryptography that we have come to rely on. And again, this idea that cryptography is predicated on hard problems. Well, if a sufficiently powerful quantum computer comes to exist, some of those hard problems stop being hard problems. And you could imagine this would be bad. And so while it is uncertain that a sufficiently powerful quantum computer could ever come to existence at all, we are investing for the long term with the rest of the industry and the rest of the academic cryptographic community to make sure that even if far into the future, such an algorithm becomes possible to run on a sufficiently powerful quantum computer, that we can still protect your data. So this idea of very large quantum computers means that the horizon of how long we expect to protect this data becomes very relevant. And again, if it's temporary credentials that themselves become invalid after a period of time, you might not need incredibly long-lived encryption. Same with earnings reports. Earnings reports might be secret until you deliberately make them public. But there's an existing continuum here. And as we push out into the future, The nature of the data being protected requires us to take seriously the possibility of this sufficiently powerful quantum computer. And so you could imagine certain governmental secrets or trade secrets need to be safe, but maybe not for the rest of time, not until the heat death of the universe. But personal information, financial records, biological information, health information must be protected indefinitely. And so when we think about the horizon for the possibility of a sufficiently powerful quantum computer coming into existence, where we could use one of these algorithms that we've known for years, common one is called Shor. Shor's algorithm undermines some of the hard problems in asymmetric cryptography. And so these hard problems listed here up top no longer are hard if this possibility comes to fruition. If the world, if the industry is able to construct a sufficiently powerful quantum computer, so we can no longer depend on these hard problems. So what do? It's a very serious problem. Well, we're developing new types of cryptography. This idea of quantum safe, or at least quantum resistant algorithms. And because we can no longer rely on those hard problems, we have had to come up with new types of hard problems in the cryptographic community. NIST, the American National Institute for Standards and Technology, has been doing a bake-off for years now. They started with maybe a dozen, they're down to just a couple. One of our algorithms is actually still in the race. And this, again, is necessary because it's so hard and it requires so much time to ensure that these algorithms are truly trustworthy, that these algorithms are truly safe. So there's a transition timeline ahead of us. The entire industry is going to move towards this. And as you build on AWS, and as you invest your time and invest your firm's resources to come to trust AWS and to rely on what we make available to you, like the Nitro cards, I again offer you that we are thinking for the long term, that we have invested very deliberately and very carefully to ensure that your data remains protected decades and decades and decades into the future, including a potential future with a sufficiently powerful quantum computer. So what are we doing about it? Well, as it turns out, we're doing a lot. This is a very, very serious thing for us. It's a very serious thing for all of cryptography, for any cloud provider, for any computer provider, for any cryptological system provider. So we've been working on post-quantum standards with NIST. One of my friends, Matt Campagno, one of our chief cryptographers, he and I are giving a talk later today at 5 p.m. About the future of quantum migration. We're investing in not only quantum safe cryptography, we've actually built and delivered some of this into production today. So you can kick the tires on it at a minimum. And if your board decides this is scoped into your threat model, you can even begin using post-quantum algorithms today with a few of our services, our Secrets Manager service, KMS service, the Cloud HSM service. And I can tell you, we are also going to be bringing it to our transfer family. Our managed SFTP and SCP capabilities are also going to be enabling quantum safe algorithms. Because again, the data you might be transmitting could be vulnerable over time. Now, it's important to understand that the cryptography that is undermined by this idea of a quantum computer is asymmetric. For symmetric cryptography, which is done for bulk encryption, the keys are okay. The keys are going to be safe. At worst, it halves the bit size for something like AES. So instead of AES 256, you end up with the strength of AES 128, which I assure you is still incredibly strong. But key agreement and signing become vulnerable. So let's talk about something else. Let's talk about IAM. You use IAM every day. As we speak, there's 1 billion IAM transactions per second, which is a weird, dumb number. 1 billion per second. So when we talk about Amazon Prime Day and we say, oh wow, at Prime Day we did so-and-so number of DynamoDB transactions during Prime Day. Every single one of those resulted in an authorization. The way IAM is built is that there is no continuous entitlement, that every single API call is independently authorized. There are no bearer tokens. There is no API key that gets sent on the wire as just a little flag. Look, I have this string of numbers. That means I can do the thing I say I can do. A lot of traditional APIs work that way. IAM does not. IAM is deliberately designed for continuous authorization. And the way IAM works when you form a request to an AWS API uses a form called SigV4, the signature version 4. And again, if you're a super nerd, you're my people, I encourage you to go online. There's a lot to learn about how SigV4 really works. But these are the important highlights, the characteristics of it. And we designed this thing years ago. And as it turns out, we kind of got it right, which is pretty cool. So we never put the credentials on the wire. We never have continuous entitlement. We never have an indefinite period of allowing an operation. Again, every single API call, 1 billion of them per second, is independently authorized. 1 billion, it's a weird number. So this idea of SigV4 comes from a long heritage of computer science here at AWS. I encourage you to check out online, again, if you really want to get into it, one of our distinguished engineers, Colin McCarthy, has a really great explanation. But the important part here is that the API calls that you make are scoped down. Not only do you not put your credentials on the wire, we use a series of elaborate cryptographic operations, simply known as HMACs, to scope down the signature on the request that isn't an entitlement to everything. That would be bad, that would be dangerous. So when you make an API call, it's actually scoped down to a particular service in our particular region on a particular day that's time-bound. This prevents replay attacks and, again, really promotes this idea that your credentials are not available to be compromised because they're never transmitted. Very, very powerful stuff. And again, you're using this every day, and maybe you never thought hard about it. That's good. It's cool that you can receive the benefit of something like this, just like the Nitro system, without a lot of specialized knowledge. But again, if you're kind of a nerd, it's really fascinating stuff. Speaking of IAM, I want to talk about this idea of principle of least privilege. We know this is hard. We know that least privilege often means maximum effort. But the truth is we take this deadly seriously because we use IAM. We use IAM for ourselves, and we often use IAM on your behalf. And so when you do something like attach a volume to an EC2 instance, and that volume is encrypted, you have to have both authorization to call EC2 attach volume, that particular API action, but there's another authorization you must have, and that is to use the key, the root key that lives in KMS that protects the volume key, which is unique to the individual volume. And you may wonder, and maybe you don't, because otherwise it just works. But when it works, how is it that EC2 is permitted to use your cryptographic key material to unwrap the keys that protect your volume? This happens automatically. You don't see it, you don't smell it, but you can inspect it if you look at things like CloudTrail. And if you look at something called the grant on the KMS key. And this is pretty in the weeds, but I want to point out some interesting details where how we do this. The bad version would be, oh, I added a line to the key policy that says, oh, EC2 can use the key. Call it a day. That's not great. You kind of probably don't want our service to have indefinite access to use your key material. And even if you did, it seems clumsy. It's very coarse-grained. It's not intentional. The word we really use here is deliberate. It's not deliberate. And so the way this actually works when you attach a volume to an EC2 instance is that we create a grant. A grant is a unique type of permission that's specific to KMS, but this is the policy language used to express that entitlement. And I want to point out two things to you. Number one, that the principal using the key material, the actor, the principal using the key material is not all of EC2, it's scoped down to that particular instance. That's what this box there, principal scope to a specific instance. It's that one computer receives the authorization. And even then, the authorization is not to do whatever they want with your key material. The authorization is scoped down to that particular volume. So when you permit EC2 to use your key material on your behalf to decrypt the volume that you mean to attach to the computer, we do so in a really narrowly scoped way. And it's very, very deliberate. I mentioned earlier this idea of provable security. And provable security has been at the heart of a lot of interesting innovations. I'm going to give it back to JD to talk about automated reasoning.
So, we started out this talk, we talked a bit about some of the themes we were going to discuss with what was behind the scenes. And we expected to find some rigor. But I think we've uncovered a few other themes. Some of them include security at scale. And as Peter mentioned a few times, they are investments and innovations that ultimately are things that our customers don't need to worry about. They get the benefit of them largely automatically. And I think that provable security and automated reasoning is a fantastic example of where a number of the innovations we talked about today come together. So what is provable security? I am not a mathematician. I am not going to go super deep here, but it is fundamentally the idea of using mathematical logic to prove that your systems carry the desired security properties that you intended. Right? By proof here, I am referring, of course, to things like a Pythagorean theorem, right? A right-angled triangle that a squared plus b squared equals c squared. How did Pythagoras do this? I don't know. I am not a mathematician. But what I can say is it's highly unlikely that they went through the brute force mechanism, right? What Peter described earlier of trying every single triangle that could possibly exist and seeing what happened, right? It's the idea of using mathematical logic to be able to make a declarative and broad statement that will hold true across all possibilities. Automated reasoning is the use of algorithms to find and audit proofs in mathematical logic. So using provable security and automated reasoning, we've found that we can deliver a tremendous amount of security value to our customers, right? Using automated reasoning, we consider all possible executions, all possible requests, and all possible configurations of a system mathematically, and are able to reason about the properties of that system. So automated reasoning allows us to infer future behavior of our computer systems. We're able to understand what a system might do under some circumstances, but not all. We're able to understand what a system will do under all possible circumstances as a matter of mathematical proof. And we're also able to determine what those systems will never do. Now, this is a broad and kind of abstract concept. We have a bit of time left together, and I'm going to run through a few of our, let's say, greatest hits. So provable security actually powers a number of customer-facing AWS features. Things like Code Guru Reviewer to find security problems in your code. IAM Access Analyzer, which allows you to compute over IAM policies to determine things like who is able to access a particular resource. The ability to simply, with a click of a button, block S3 public access as a matter of mathematical proof. Some of my favorites actually are VPC Network Access Analyzer, Reachability Analyzer, and Inspector Network Reachability, which allow you to reason about multiple connected VPCs and deeply complex network relationships as a matter of math. In addition, we have things that are kind of going behind the scenes, and these cover a number of the topics that we talked about today. Provable security is a driving force behind things like identity, deep in the Nitro system boot code, the API layer that I mentioned on the Nitro controller. We use it for analyzing operating systems, networks, virtualization systems, cryptography like with S2N TLS. And we're also doing a tremendous amount to publicize the work that we're doing in the academic literature and contribute back to that discourse. So with that, I say thank you very much. It was a pleasure to be with you here today.